Hey, AP Chem Rockstars, here's what we got going today. We are jumping into 3.7, which is solutions, and we talk about mixtures as well. So, jumping right in, we're actually going to do a quick review of matter. There are two types of matter, two main types of matters and way it can be broken down. The first one, put that over here, is pure substances. All right, so we've got our pure substances here. And within our pure substances, there are two major types of matter, or two major types of pure substances. Our first one is the simplest form of matter. These are our elements. All right, so they have all the same atoms, so they're the same throughout, right? And then we have, over here, we have our compounds. And remember, our compounds are made up of multiple atoms, but they're chemically combined, so they're always the same. They always have the same ratio of elements in them. So these guys are always the same. The pure substances are always the same. No matter where we are, they're always the same. So then we go to the other side, and this is where we have our mixtures. And this is actually what we're going to be talking about just a little bit today. We have our mixtures here, and there are two big types of mixtures. So mixtures are not the same throughout. So our two big types of mixtures are, our first type, and this is the one we're going to be spending time with, is our homogeneous mixture. Remember, homogeneous means same, so it's the same throughout, right? And another name for a homogeneous mixture is a solution. So we're talking about making solutions, and solutions are homogeneous mixtures. The other type of mixture is our heterogeneous mixture. All right. And in a heterogeneous mixture, what we have is, obviously it's not the same throughout. It won't always be the same. Like when I make my Kool-Aid, it's always the same. All right. When I look at like pond water, it's not the same. Or here's my perfect example, right? We get chocolate chip cookies. Sometimes there's a few chocolate chips and sometimes there's not. So that's heterogeneous. It's not always the same throughout, but on homogeneous, it looks the same throughout. There are two other parts of heterogeneous, just to throw these in here so you've had experience with them, or at least have seen them before. We have the first one here is a colloid. All right. And the second one, put it down here, is a suspension. And these are distinguishable only by size of particles, all right? So depending on the size of the particle will tell you if it's a colloid or a suspension. You'll get more into that into a later chemistry course, so we're not going to hit that one too hard here, all right? So remember, today our key is, our focus is, we're on homogeneous solutions, okay? So let's go ahead and jump right into our vocabulary. Our first one is, our solution is obviously a homogeneous mixture, which means it looks the same throughout and is the same throughout, right? So we're talking about having the same concentration. So that's like our Kool-Aid. It tastes the same at the top and the bottom, provided we have done some shaking, right? Then we have our solute. Solute is the one being dissolved, is the substance being dissolved. All right. And usually it's the one in the lesser concentration, but that's not always true. Then we have our solvent. This is the one doing the dissolving. And again, usually it's in the higher concentration, but not always. Then, kind of as an aside, we have water, is called the universal solvent. That's because water dissolves a lot of things. All right, and we use water. Most of the time we're going to be talking about water as the solvent, so that's kind of what we usually talk about. But sometimes when we have nonpolar substances, going back to our like dissolves like discussion, sometimes we have to use like an alcohol to dissolve like a nonpolar substance. But again, I digress. Going back, we have aqueous solution, and this just means that it's dissolved in water. So aqueous solution and our universal solvent, kind of what we got there. Now, if we move on to molarity, learning molarity, it's moles of solute over liters of solution. This is on your sheet right there, but it looks like this in our equation sheet, so kind of be aware of that. What we have here is we have molarity of a solution. The other thing, kind of what we need to talk about here, is sometimes we have to go a little bit further. So sometimes we have to go from moles to grams, and we do that by multiplying by the molar mass. Or sometimes, like this first problem, we've started at grams and we have to go to moles, so we'll have to divide by the molar mass. So we have to remember how to do the molar masses. Today for our practice problems, I already found them for us, but I showed how we got there. So let's take a look at this. We're looking for the molarity of a solution that contains 25.5 grams of KBr and enough water to make 1.75 liters. So we're looking for molarity. So our formula, molarity equals moles over liters. All right. Molarity is our question mark. Moles here. We know we have 25.5 grams of KBr. All right, and we can convert that to moles by dividing by the molar mass, which I found for us a little bit earlier. Hopefully we remember how to get there. All I did was take 1K times the atomic mass and then 1 Br times the atomic mass, added them up. All right, so here we're going to take 25.5 and we're going to divide by 119. And that's going to give us in moles 0.214. Let's keep 286 just to make sure we have plenty. That's our moles. Then we go to liters, and that one's already in liters, although sometimes we'll have to go from milliliters to liters. But pretty simply, we're just going to take that 0.214 and divide by 1.75. And I left that 0.214 in my calculator, so all I had to do was take divided by 1.75. And keeping 3 sig figs in our answer, we get 0.122, and our label on molarity is capital M. It must be a capital letter. Sometimes it might be helpful to add like the KBr, the substance we have, but it is not necessary. The biggest thing we have to have is that capital M. All right, so our next example is we are at molarity in liters and we're trying to figure out grams. So we have to rearrange our formula just a little bit. And we do that by molarity is going to be now equal to moles is going to be equal to molarity times liters. So what we do there is we're going to take 0.758 and we're going to multiply that by 1.55. And that'll give us our moles of sucrose. And so our moles of sucrose, 1.1749. Again, that's moles of our sucrose C12H22O11. So that one's a little more aggressive as far as our molar mass, right? But luckily, again, I found that one for us. So we're going to put that on top, 343.87 grams, and then 1 mole on bottom. So if I multiply that times 343.87, that'll be how many grams are dissolved in that solution. So we've got 404 grams, if we keep 3 sig figs, of our sucrose are dissolved in there. So hopefully that makes sense. That's kind of the calculations behind making a solution. But as we move on, we now need to talk about how would we actually make a solution. All right, so I'm going to shrink this just a little bit here. Hopefully you had it long enough so you could keep it, but I'm going to make it just a little bit more tiny. All right, so we can talk about making a solution here. So when we're talking about making a solution, we're going to use one of these little things, and this is called a volumetric flask. All right, volumetric flask. And what this flask does, if you look at it closely, this line right here is a graduated line, so it measures precisely to that one. This looks like maybe a 250 or a 500, so when you fill it up and the meniscus of the solution is right on that line, you have exactly, let's say 500 mils or 250 mils. All right, so that is what you would use to make a very precise amount. Remember, beakers and Erlenmeyer flasks are not very accurate, and we never really want to make a solution in a graduated cylinder. All right, so if we're making like that sucrose solution, all right, let's take a look at that. If we're making the sucrose solution, what we would do is we would add just a touch of water to the bottom of this volumetric flask. All right, we add a little bit of water to the volumetric flask. Then we would put our sucrose in there and stir it up. Now we do that because if you see like this long neck, this long thin neck here, makes it really hard to mix. But if we like put our solution in there and then shake it up while we still have some room in there, it actually mixes a lot better. Then we're going to fill it up to that line. And the key on filling it up to that line, first of all, we definitely want to use distilled water on this. All right. Then we're going to use, as we get into the neck, my suggestion is that we change to a bottle, like a dropper bottle. All right. Because if you go past that line, you are just kind of out of luck and you have to start all over. Okay, does that make sense? And so that would be the steps we would take on how to make a solution. So kind of quickly to review. First, add a little bit of water on the bottom, then add our solid, then swirl around, then fill it up to the line, right, where the meniscus hits that line with distilled water. Okay, awesome. Let's roll on. Now we have our solution dilution formula. This one is M1V1 equals M2V2. We have seen this already, and it's very, very simple, hopefully. So really, let's just check this out. And then we just kind of write what we have, and make sure your molarities go with the molarities that you know. So you have 15 molar, and then we have 0.2 molar, or 0.2 liters. Those go together. And we're trying to make a 3 molar. All right, we're trying to make a 3 molar solution, and we want to know how much we need to get there, or how much will we need to dilute it to kind of get there. So that's our question mark. All right, and so really we just take 15 times 0.2 equals 3 times V2, and then we just solve by dividing each side by 3. All right, and this is hopefully very simple. 15 times 0.2 divided by 3. That's our answer. We should dilute it to 1 liter. V2 is 1 liter. All right. If we keep our sig figs, we should probably have a couple more there. 1.00 liters. All right, pretty simple there. You'll get some practice on that in your homework today. Now, the last one. Now, if we're making a dilution, a lot of times this happens with acids and bases. And so the biggest key here, oh my goodness, this is so important. You're never going to take like a strong acid and add water to it. All right, because when you dissolve an acid in water, it is a very exothermic reaction, which means lots of heat is given off. And if you do that, and you don't have very much water in there, you could have a small explosion or your glass could crack. It's really not a good thing. So we always, always, always add acid to water. All right, we never add water to the acid. Okay, but the same steps apply here. We've got our little volumetric flask. So let's say we have a strong acid, right? And we're trying to dilute it kind of like what we did up there. Our first step would be add some water, get some water in there, right? Then we add the acid, all right? Then we add the acid. Do a little swirl, and sometimes you might want to even let it cool down just a little bit, depending on how strong the acid and how much you're putting in there. And then you go back to the water and you fill up to the line, right, where the meniscus hits the line. Okay, thanks. See you next time.